Okay, so yesterday, guys, we were working on work energy theorem. Okay, so work energy theorem says that work, oh, don't want yellow, that doesn't make any sense. Okay, that work is a change in mechanical energy, right? And mechanical change means final minus initial. So we can expand this out to work is our final mechanical energy minus our initial mechanical energy. Okay? Everyone okay with that so far? Delta always means change, right? It always means final minus initial. And we know from Science 10 that mechanical energy is the sum of an object's kinetic and potential energy. So we can expand this out to say that that means EK final plus EP final minus EP initial plus EK initial. Right? Saying the same thing here over and over again, right? But I'm just expanding it out. Work is a change in mechanical energy. Right? Last year in Science 10, you never had to do any problems that involved both kinetic and potential energies changing at the same time, but the reality is that happens more often. Okay? In Science 10, you only had to do one that would be like a change in potential or a change in kinetic. Here it could be both. Right? And what's the other way to calculate work besides the change in energy? Right, force times distance. Okay, so work energy theorem breaks down to this. If there's a force acting through a distance, it's going to do work. That work is going to change the mechanical energy of the object being pushed or pulled. That looks like this mathematically. Okay? So, here's what I want you to do. I want you to write down this example. Okay? Call it work energy theorem example number 1. Okay? I'll give you a minute to get it written down along with the diagram. Okay, just draw a rough version of the diagram there, and then we'll work it through. Okay, so in this situation, we've got a block at the bottom of a ramp. Okay, it's moving at 1 meter per second. A little while later, it's at the top of the ramp, and it's moving at 4 meters per second. It is also now 0.850 meters vertically higher than it was at the beginning. Okay, now, does it have more energy at the top than it had at the bottom? Definitely, right? Not only is it moving faster, which means it has more kinetic energy at the top, okay, it's higher at the top than it was at the bottom. Okay? The only way for its energy to change would be for what to be done to it? We're pushing it up. It starts at the bottom, ends at the top. If it was the other way, absolutely, we'd let it go. Okay? But the only way for it to go that way is if I do work. Okay? I have changed the energy of that block. Okay? And it has accelerated up the ramp. Right? It's not going to do that on its own. That's going to require a force to be exerted through a distance. Agreed? Okay. So we are definitely then looking at a situation where work is being done. That's the first part of solving a question like this, is identifying this is not a Newton's question. Okay? This is an energy question because we're talking about something having work done to it. Okay. So now what I've got to identify is what kind of energy does it have at the beginning, and what kind or kinds of energy does it have at the end? And then maybe even look at calculating those things, right? The question wants to know what's the work done moving the block up the incline, okay? So if I want to find work is either force times distance, I don't have either one of those things in this question, or it's a change in energy. That I could probably calculate because I know heights and I know speeds. Okay, those things can help me to get gravitational potential energy and kinetic energy. Agreed? Okay, so let's just kind of run through this here. Okay, so I'm going to take out this part here, this bottom one that I put on a minute ago. I'm just going to take that out. Whoa, come on. Okay, so I know that the work being done is the change in the mechanical energy. That's what this statement says. All right, the things I know are VI. I also know HI. What's the initial height of that box? 0. It's at the bottom of the ring. Okay, so I know the initial height is 0 meters. All right, I also know the final height. This would be HF because it's the change in height, and it was 0 at the beginning. Okay, and it's final speed. Okay, they use 2 and 1. We use I and F. Okay, 4 meters per second up here. I also am told the mass. It's 1.2 kilograms. Okay, and can I assume that this is on Earth? Okay, so what's G? 9.81. Okay, so looks to me like I've probably got enough information to calculate initial kinetic energy, initial potential energy. What's the initial potential energy in this situation? 0. It's at the bottom of the ring. Okay, final potential energy and final kinetic energy. I've got mass, VI, VF, HI, HF. I can do this. All right, and then that'll let me calculate the work. All right, got to expand this out a little bit more. Kinetic energy is 1/2 mv, in this case, final squared. Final potential would be m times g times h final, minus m times g times h initial. Do I even need to write that in this situation? Because hi is 0, so what's m times g times hi? 0. Okay, we'll cancel it off in a minute. Plus 1/2 mvi squared. So like we said, that's 0. So okay, I'll just get rid of that, and I'll have my final energy minus my initial energy. The object only has kinetic energy at the beginning, and not much of it because it's not moving very fast. Okay, so now that calculates work. I just have to plug in my numbers. Okay. So 1/2 times 1.2 kilograms times 4 squared. So my final kinetic energy plus 1.2 times 9.81 times 0.850, my final potential energy, minus 1/2 times 1.2 times 1 squared, my initial kinetic energy. Okay, I probably should have fired up my calculator before that. Okay, so we are going to have 0.5 times 1.2 times 4 squared plus, okay, plus 1.2 times 9.81 times 0.85. All right, so there's my final. Okay, and then I'm going to subtract from that 0.5 times 1.2 times 1 squared. Okay, so according to this, 19 joules worth of work must have been done on the block to accelerate it up the ramp. Okay, and that would make sense. It should be positive. I mean, it has more energy at the top than it had at the bottom. Okay, that would definitely require work. It wouldn't do that on its own for sure. Okay, so our final answer there would be 19, what have we got, 3 sig digs? Yeah, 19.0 joules. Okay. a part B to that question could have been they give you the length of the ramp and ask you to calculate the force, or they give you the force and ask you to calculate the length of the ramp, okay? Or they give you force and distance and ask you to calculate the final height. Okay, so you could calculate the work and then solve for some part of it along the way. That's what we're going to be working on today, is doing problems like this, which probably look a bit familiar. They kind of look like a conservation of energy question from last year, okay? And they're close. In a conservation of energy question, the work would be 0 because the work doesn't change. Okay, so it kind of looks like it sets up that way. This says there is a change, and whatever that change is the work that was done. Okay? So you could be asked to solve for any part of this string here. You could be, given the ability to calculate work and asked to calculate final speed or final height or initial speed, provided you're given the other things. Okay? So it breaks down to it's an algebra exercise as long as you're able to identify the types of energy involved. Okay? All right, let's have you guys try 1 and 2 for right now. Okay, so write those ones down and give them a try. Okay, and we'll go through them together here in a few minutes. All right, so in our first one, we've got a cliff. Okay, and then we've got the person at the bottom of the cliff. So top of the cliff is our initial position, okay? And VI would be 0 up there because they're not falling yet. And their height is 25 meters. So HI would be 25.0 meters, all right? Down here at the bottom, okay, their final height is going to be 0 meters because they're at the bottom. And their final speed is 5 meters per second. Okay, I'm fairly certain that means that this person did not fall, right? If the person had just fallen, this would have been a law of conservation of energy problem. And their speed would be a lot greater than 5 meters per second. Okay, so obviously, some of their initial mechanical energy, due to their height, has been turned into something else. Okay, if you've never rappelled, one of the things you have to be careful of when you rappel is the carabiner that the rope is running through. You use it as a brake. Okay, you have the rope angled, and you're basically increasing the normal force between the carabiner and the rope in order to increase what force? All brakes use friction. Yeah, so you actually have to be very careful that you don't accidentally touch the carabiner. It is hot enough to burn you. Pretty bad, actually, which is why you see, people using gloves. They don't want to get rope burn, but they also have, gloves that go back to here sometimes so that they don't accidentally touch the carabiner with their forearm and get burned. All right, so the carabiner is going to get hot. Well, if the carabiner gets hot, the only place for it to be getting that energy from was the initial energy of the person rappelling. That's why they have less energy down here. The difference in energy between top and bottom is the work done against friction on the carabiner. They turned their mechanical energy into heat that went out into the surroundings. Does that sort of make sense? That's the kind of in our head analysis that has to happen before we start this process. Work's a change in mechanical energy. Okay? Work is our final potential plus our final kinetic minus our initial potential plus our initial kinetic. Now that I've, in my head, analyzed the situation, can I get rid of any of those energies? Well, pretty sure I can get rid of this one. Since the final height is 0, I can't fall any further, so I don't have any final potential energy. Okay? And initially, I'm not moving, so that means I don't have any kinetic energy either. Well, that just means then that my final kinetic minus my initial potential tells me the work. Okay? What throws people on this is that they get a negative number. Okay? If you got a negative number, you did it right. This person lost energy. That's negative work. Okay? The energy went into the surroundings. If they asked about this from the surroundings perspective, the number would be positive. Okay, so we're going to have that work equals 1/2 mv final squared minus m times g times h initial. Plug in our numbers. 1/2, the person is 72 kilograms. Okay, times 5 squared minus 72 times 9.81 times 25. Okay, so 0.5 times 72 times 5 squared minus 72 times 9.81 times 25. Okay, that's a lot of energy. Okay, that carabiner is going to be really, really hot. Okay, don't touch it. Okay, that's a lot of joules. Okay, what do we got, 3 sig digs there? So 1.68 times 10 to the 4 joules worth of energy, worth of work done to slow that person down. Okay, that's what you want. You want the friction to do work and take away your energy. All right, everybody okay with that one? How many people are done number 2? Okay, give me a few minutes on number 2. Okay, so number 2 is actually only very minimally a math question. The rest of it is kind of a, we need to see a relationship kind of a question. Okay, so if I exert a force of 150 newtons over 5 meters, can I calculate the work? All right, that's a science 10 question, right? Force times distance. Okay, well I can get that then. Okay, so work equals force times distance. I'm just going to go 1,500, or 150, sorry, times 5 should be 750, right? Is that right? 750 joules? Okay, so that's how much work is done. That's a simple calculation. Okay, for part B, what's the change in gravitational potential energy? Okay, well, what's my initial height? 0. I have to assume that, right? It's lifted from the ground, okay, to a height of 5 meters. So my change in gravitational potential energy would be mgh final minus 0, because I don't have any initial, it's on the ground initially. Okay, so that's just going to be then 9 times 9.81 times 5. Okay, so I get 441.45. Okay, I did 750 joules worth of work. My potential energy only changed by 441.45 joules. Where's the rest of the work? Can work change both kinds of energy?
Please excuse the interruption. Can anyone who did not get a photo taken on the original picture day please come down? Even if you don't plan on ordering pictures, we need one for the yearbook. So please come down and have your picture taken in the cafeteria. Thank you.
Okay, so I have to assume then that the rest of the work changed some other kind of energy. Okay? Energy can't be created and it can't be destroyed. It has to do something. All right? So we have to assume then that it changed another kind of energy. Since there's no mention of friction or other non-conservative forces, we have to assume the rest of this changed the kinetic energy. Everybody okay with that? All right. So the change in kinetic energy then, okay, is going to be 750 minus that number, whatever is left. Okay, so there's my change in kinetic energy, 308.55. Okay, so that means I didn't just lift this thing, I accelerated it upwards. Would you agree? Okay, because there's a change in kinetic energy, that means the thing sped up. Okay, it didn't slow down, it sped up because it's positive. Okay, does everyone follow how I arrived at C? Okay, all right. Now, for number 3, this is the part, okay, that you guys haven't done yet, so I'm going to give you a minute to try this. But this is the relationship part. that I want to really point out to you. Okay, so number 3 is kinda Newton and kinda energy together. I want to show you the relationship between what happens with Newton and what happens with energy. All right, so see if you can do number 3 here, and then we'll talk about why it works a certain way. Okay, so I'll give you a couple minutes there. So the first thing they want you to do is do a Newton's second law problem with this situation. Okay, so we've got our 9 kilogram mass here, we've got 150 newtons acting up, and then since it's a 9 kilogram mass, we have 9 times 9.81 going down. All right, so 88.29 newtons. All right, so at this point then, we can calculate the net force. We just have to go 150 minus 88.29. All right, so the net force in this situation is 61.71 newtons. If there's a net force, what does it cause?
Please excuse the interruption. Could we get the grade 10s who need picture retakes from last names S to Z down to the cafeteria for your photos? Thank you.
Okay, so net forces cause objects to accelerate. Acceleration is a change in velocity. If your velocity changes, does your kinetic energy change? Okay, so net forces cause changes in what kind of energy? Kinetic. That's why what happens in B, where they ask you, calculate the work done on the mass by the net force, not the total force, the net force. Okay, so if I take that 61.71 newtons and I multiply it by the 5 meters, lo and behold, I get 308.55 joules. Exactly the amount the kinetic energy changed by. Okay, so what's the connection we're supposed to make here? The connection we're supposed to make here is if there's a net force, there will be a change in kinetic energy. If there's no net force, then you're only going to change potential energy. The object will move upwards at a constant velocity. Okay? I didn't need all 150 joules, or sorry, 150 newtons to lift the object. Okay? It was more than enough. I only needed 88.29 newtons to lift the object. That would have lifted it at a constant speed and changed only its potential energy. It still would have been work, but there'd have been no net force, and thus no change in kinetic energy. All right, so net forces cause accelerations, which cause changes in kinetic energy. In other words, they do work. Okay, everybody all right with that connection? Okay, write this one down, give it a try. Okay, now keep in mind that it says it is pushed down the ramp. Okay, not just allowed to roll, it's pushed down the ramp. Okay, there's actually more than one way to do this. Okay, we can solve this as a work energy theorem problem, which is the way I would recommend because it's faster. Or you could solve it as an inclined plane problem. Do a Newton's second law thing, get the acceleration, do an acceleration calculation. You get the same answer. I mean, it's physics. You have to get the same answer. It's the same object. Okay, it's two different points of view. But the Newton way involves a lot more steps. It would take you easily twice as long to do it that way. All right, so let's solve it the first way. I'll kind of split the screen here. So I'll do Newton on that side and I'll do energy on this side. Well, actually, let's draw the picture first so we have it. Start that over again. Okay, so we have this ramp, okay? And we have a 1,500 kilogram car, okay, on this ramp. We know the ramp is 15 meters long, okay? And there's a force of 450 newtons pushing it down the ramp. Okay, at the starting point, the car is moving, so at the beginning, the car is moving at 1.2 meters per second, and it is 3 meters above the bottom. Okay, assuming there's no friction, how fast will it be going at the bottom of the ramp? Okay, so our final point, we're looking for VF. HF will be 0. Okay, everybody with me so far? Okay, is work being done here? Right, there's a force pushing this thing down the ramp, in addition to F parallel and all of that kind of stuff that would also be going down the ramp. Okay, well then, let's start this from an energy perspective. Okay, work's a change in mechanical energy. This question actually gave me both the force, okay, 450 newtons, and the distance, 15 meters. All right, so I'm going to go, okay, force times distance equals, okay, EK final plus EP final minus EK initial plus EP initial. Okay, would that be true for this situation? I can even make it simpler because EP final is 0. Final position is the bottom of the ramp. Okay, so I can even take that part out. Okay, so I am looking for VF. So I can still say this, FD equals 1/2 MVF squared, right? I'm looking for this part here. Could I take this whole thing over to the other side? I could, right? I mean, when it comes right down to it, what I'm doing here is saying that work equals the final energy minus the initial energy. What I'm looking for is part of the final energy, so I can add the initial energy over to the other side. Okay, so that's what I'm going to do as my next step. I'm going to say force times distance plus EK initial plus EP initial, okay, equals 1/2 MVF squared. Okay, everybody okay with what I did there? The change in energy, work, plus the initial energy should equal the final energy. That's what I'm saying. Is that okay? Initial plus change should equal final. All right. Now, I just have to bring the 1/2 and the M over to this side, and I'll have VF alone and then square root. Agreed? Okay, so I'll have force times distance plus 1/2 MV initial squared plus M times G times H initial divided by 1/2 of M equals VF. Okay, just manipulated for VF. Okay, plug in my numbers and solve. Okay, so that's going to be 450 times 15 meters plus 1/2 times, what was the mass of this car? 1,500, right? Yeah. 1,500 times, the initial speed was 1.2, right? Yeah. 1.2 squared plus 1,500 times 9.81 times 3 meters divided by 1/2 times 1,500. Okay, so I just plugged in my numbers. That should give me the speed at the bottom of the ramp. Okay, so 450 times 15 meters. Okay, so there's the work done by that force. Okay, plus 1/2 times 1,500 times 1.2 squared plus 1,500 times 9.81 times 3. Okay, divide that by 750, half of 1,500. Okay, and then square root that. Okay, so at the bottom of the ramp, it's going 8.3 meters per second. That seems fairly reasonable. Okay, it's being pushed down a 15-meter long ramp. It seems right. Okay, 8.3 meters per second. Okay, so this is the work I had to do to get there. Okay? I basically had to do force times distance equals the change in energy and solve for VF. Okay, so let's say 3 steps. That's basically what that came out to. All right, is there another way for me to solve this? Okay, did anyone do this as a Newton question with an inclined plane? Yeah? Okay, do you still get 8.3? No? Okay, we will. I'll show you. You probably just forgot one of the forces. Okay, so if I do this as a Newton question, I know the height of this ramp, okay, 3.0, and I know the length of this ramp. Can I get the angle? I can. And I'm going to need that if I'm going to do this as an inclined plane question. All right, so there's my first thing. I got to calculate theta. That's going to be sine to the -1 of 3 over 15. Okay, so first calculation, I got to calculate the angle. Okay, so the angle is 11.5 degrees. Okay, now that I've got that, now I can do this. I can do this triangle. Okay, whoops, sorry, that angle's got to go that way. All right, and this is 11.5 degrees. Okay, so now I got to calculate FG. F times G, so 1500 times 9.81. Okay, so 14715 newtons. Okay, now I got that. Now I got to get F parallel. Okay, so that's another calculation. Okay, sine of 11.5 times 14,715. Okay, sine of this number. Actually, I'm going to use the real number. Whoops. Try that again. Times 14715. Okay, so F parallel is 2,942. Also acting down the ramp. Okay, so now I've got that number, 2,942 newtons. Now, there aren't any other forces, so now I can calculate net force. So 2,942 plus the 450 newtons acting down the ramp. Okay, so that number plus 450, there's my net force.
Please excuse interruption. Could all grade 11s that are wanting picture retakes with the last name starting with A to M come down to the cafeteria for your pictures? Thank you.
Okay, 3,392 newtons down the ramp. Now that I have the net force, what can I calculate? Acceleration. Okay, so acceleration is F net divided by mass. So 3,392 divided by 1,500 kilograms, okay, will give me the acceleration. Okay, so the acceleration is 2.26 meters per second squared. Down the ramp. Okay, now that I have that, okay, now I can go, all right, I've got acceleration, I've got VI, I'm looking for VF, and I have distance. So now I can solve for VF if I use this formula. VF squared equals VI squared plus 2 times A times D. And I've got a square root of that. Okay, so VI squared plus 2 times A times D. All right, plug in my numbers here. What was VI again? 1.2? Yeah, okay. So 1.2 squared plus 2 times 2.26 times 15 meters. Okay, so square root of 1.2 squared plus 2 times that number there, okay, times 15 meters. Oh, yeah, there it is. Same number. For the love of God, don't do it that way. Okay, I mean, that was a lot. I went a lot faster. I did the work a lot faster, but that was a lot more steps. Would you agree? And every step is a chance to make a mistake, even if it's as simple like I pushed the wrong button on the calculator, right? This way only involved me having to type stuff into my calculator really once. Okay, way better if I can recognize that it can be a work energy theorem question to do it that way rather than a Newton question. Do both get you the same answer? Seems like it, but one is a heck of a lot less work. And on a test where time is a factor, I do it the quick way. Okay, but again, we're back to that. There was a change in kinetic energy here, right? I used the net force to get it. I still get the same answer. Okay. All right, try this one. Similar thing, okay? So you got a crate rolling along a conveyor, okay? It's angled at 15 degrees below the horizontal, so these crates are rolling down this conveyor, okay, so downward. Crates are moving at 0.75 meters per second at the top, okay? Accelerate to the bottom, that's 2.5 meters below the top, vertically. That's not the length of the conveyor, okay? There is a force of friction of 150 newtons along the length of the conveyor. I want to know how fast they're going at the bottom of the conveyor. Okay. This is a pretty involved one. Okay. About as involved as they would get. Let's get the setup done here. Okay, so we got a crate. Okay, at the top, its initial position anyway, 200 kilograms. So here, its initial height is 2.5 meters, and its initial speed is 0.75 meters per second. The second point where we're dealing with it is at the bottom. So our final height is 0 meters. Okay, obviously it's still 200 kilograms. Okay, and we're looking for VF here. We know that it is 15 degrees below the horizontal. So that means that angle is 15 degrees. If that angle is 15 degrees, so is this angle. Okay. Now, I know this height here is 2.5 meters. I know the force of friction that's acting on this thing is 150 newtons. That is going to change the energy of the crate as it goes down the ramp, right? If this ramp was frictionless and the thing went down, it would be going faster than in this situation that has friction, agreed? And the only reason for that is that it's got to lose energy to friction as it goes down the ramp because it's going to do work against friction along the length of the ramp. What do I not know about this ramp? The length. Can I find it? Okay, that would be the first thing I would do, okay, is find the length of the ramp because you can't find the work without it. The work is the force of friction times the length of the ramp. That's why the box loses energy. It's doing work against friction. So you need to know the length of the ramp to get started. Okay? I won't say anymore. I'll let you see if you can get it. After that, it's work energy theorem. Okay? But you need to have the work before you can do the theorem. Okay, so the first thing we need to do is, as we said, get the distance, right? The length of the ramp. So that's just a trig calculation. Okay, we're going to manipulate. The length of that ramp will be 2.5 divided by the sine of 15 degrees. Okay, so our ramp is 9.66 meters long. Okay, that is also the distance over which the force of friction works. okay? And as we said, it's the force of friction working over that distance that causes the change in energy. Okay, once you have that distance, you can do work energy theory. Okay, one more thing to think about, because this will give you a problem if you don't account for it. Force of friction, doing positive work or negative work? Negative work. Should the force of friction be a negative value? Okay. If you don't do that, your calculator will have a conniption fit when you try to calculate the final velocity. Okay? Because you can't take the square root of a negative number. Right? So you have to make friction negative, because it is. It's negative. It's working against you. Okay? It's taking energy away. So once again, there's more than one way to solve this problem. You could solve it as a Newton problem. It's in this exact situation, it's only slightly more work to do it that way. It's not as bad as the first one we did. Okay? But I would still advise against doing this as a Newton question, simply because there are ways for me to make it impossible for you to solve it as a Newton question. Okay? Just depending on the givens I give you, I could make it nearly impossible to solve it that way. Okay? And make it so you have to use the work energy theorem. So I'm going to solve it with the work energy theorem method, because that's what I've got right here. All right. Now, if I'm looking this over, okay, I know that my final potential energy is 0. We're talking about the bottom of the ramp, so that number is irrelevant. What I'm looking for is the final speed, which is part of my final kinetic energy. So can I bring this whole thing here over to this side? Just like I did in the first question. Okay, I'm going to add the initial energy to the work. Okay, so I'm going to have the force of friction times distance, the work, plus the initial energy. Okay, so that'll be dP initial plus EK initial. That's going to equal the final energy, which in this case is all kinetic. Right? Now I can plug in my formulas. Okay, and then I'll have to manipulate a tad bit more, and then I'll be able to solve. Okay, so I'll have force of friction times distance plus m times g times h initial plus 1/2 mv initial squared equals 1/2 mv final squared. All right, I want to get vf by itself. What do I do with the half and the m? Divide them over to the other side. Okay, then I can square root. Okay, so now I'm solving for VF, right? So I had to calculate the angle. That was one calculation. And then I did work energy theorem, which involved a little manipulating, right? Not a lot. Okay, so now I just need to plug in my numbers. All right, so the force of friction was 150 newtons. But we said that needs to be negative, because it's going to be doing work that takes energy away. All right, and I'm going to multiply that by the length of the ramp, which was 9.66, right? Yeah. All right, and then I'm going to add that to the mass of the crate, which was 200 kilograms, times 9.81 times 2.5 meters, right? Yeah. All right, plus 1/2 times 200 times the initial speed, which was 0.75, right, squared. And then I'm going to divide all that by 1/2 times 200. Okay, so negative 150 times the 9.66. Okay, plus 200 times 9.81 times 2.5 meters. Okay, plus 0.5 times 200 times 0.75 squared. All right, divide that by 100, because that's half of 200, and square root that. Okay, so at the bottom of the ramp, it'll be moving at 5.9, I think we only have 2 sig digs there, so 5.9 meters per second. Okay, so when it came right down to it, yeah, I had to first do a preliminary calculation where I found the angle. And then I just did work energy theorem after that. Okay, if I solve this as a Newton problem, which I could, okay, I would have to do all that other stuff again. I would have to find the weight, I'd have to find FG, then I'd have to find F parallel, then I would have to find the net force, then I would have to find the acceleration, then I would have to use the acceleration to find the final speed. Would I get the same answer? Yes, but I do a lot more steps. Okay, everybody follow me there? So it's possible to do it either way, but work energy theorem, I get it, it's new, it seems like it's long, okay, will in the end be faster and more reliable because you'll only have to do one calculation as opposed to 5 or 6. Okay. All right, how are we feeling about that? Okay, we're going to work on that a little bit more today and tomorrow. But I did want to remind you of a couple of things. Okay, the Newton assignment is due on the 24th, so on Monday, so make sure you've got that done. And then tomorrow I also want to go over your lab reports with you. Okay, so we'll get that done. I have not been able to mark them because the internet went down, and I was going to mark them in period 1. I shouldn't have left it till the last minute. I'll take that one, that's on me. Okay, so my apologies for not having them back to you for today's class, but I will have them done for you by the end of the day. Okay, which is not as fast as I like getting them back. It's usually I have them done faster than that. Okay, but yeah. Okay, see, I didn't even take my own advice. I always tell you, never leave it till the last minute, and I did, and what happened? Yeah. Fate knows when you've left things till the last minute. Okay, reminder also, guys, unit exam's going to be December 1st. Okay, so that's a week from Monday. We'll easily be done by then. We're going to work on work energy theorem tomorrow, maybe a little bit on Monday, conservation of energy next week, power, and we're done. That's all there is to it. Conservation of energy is exactly the same as it was in Science 10. EI equals EF, roller coaster questions, it doesn't change. Okay, so we won't need to work on it for too long. Okay, and then we're looking good after that, right? We should be able to get the circular motion unit done before Christmas, okay? Because it's pretty short. And then we just have simple harmonic motion and waves to do after that. All right? Everybody with me there? Okay. So my plan is to still finish with about 2 days to spare at the end of the semester, because I promised you at the beginning of the semester that I would give you the opportunity to raise your lowest exam mark. Okay, and I want to be able to keep that promise by letting you write a mock final, which does not count for your mark. Okay, it is not in any way, it's like totally no fault. Okay, but it would give you the opportunity to raise your lowest exam mark if you do better on that than your worst unit exam. Okay, but it can't hurt you to write it. It's also zero pressure. If you just show up that day and feel like not writing it, you sit here. Okay, there's no pressure on it at all. Okay, but I want to be able to keep that promise. Lots of people like to have that safety valve and be able to go, okay, I really need to raise this mark, so I want to still be able to do that for you. All right. Okay, we will leave it there for today, and we'll pick up with work energy theorem tomorrow.